So just stop that. All right. So let's clear things up, make sure that we're all on the same page about this whole how to deal with couple of rotations and translation, how to find transformation matrices from one coordinate system to another, because that's something you really have to get comfortable with. Part of it, I don't want to say it's intuition, but part of it, a good part of it is to figure out the rotations correctly. And that really, honestly, there is no formula for it that I can give you. I can probably come up with so many multiple pages of procedures that, oh, if X is here and X1 is here and X2 is there, and you want to align these axes, rotate Y. If you want to align these axes, rotate X. But that becomes overly complicated. So I suggest that you just, play around with it. You need to have a little bit of, I guess, patience with it and start thinking about different rotations, especially when we get to two rotations. One rotation is usually straightforward, but when you have to do two rotations, sometimes I didn't bring it up. I'm not going to talk about it because it makes even things more confusing. When you wanted, you have to do maybe multiple three rotations. Well, we do three rotations, but it's not really three rotations. It's just the type of joint that we're dealing with that we have to take that into account. But sometimes two axes, you actually have to do 90 degrees rotation, and things just get even more ugly. We're just going to stick to 90 degrees rotation and whatever joint we're dealing with. So yeah, that's what I was saying, that I'll just ask you to practice a little bit with the problems we have, examples we had before, the problems we went through last class, and the one that we're going to go through today, and get a sense and try different approaches. You might even find a new approach, right? I gave you two approaches for this example. And I think even for the next example, I gave you two approaches. For part A, maybe not. I only gave you one approach for part A. How about part B? Did I give you? For part B, I guess we went through one approach. I can actually talk about the second approach. And then we'll add part C to this one. I'll go over the third example that I have I want cover. So let's start with this one. So we had the frame, right? We said you can imagine that to be a simple robotic arm, right? It's a two revolute joint and one prismatic joint. Revolute joints, the rotation are represented by, it's theta 1, theta 2, but for some reason I just went with V1 and V2, so I'm just going to stick to that. V1, V2, and D3 being the translational rotation for the third joint. And we said we have these coordinates. I kind of made a mess there, so I'm not going to mess with it more. For part A, we said, well, we want to find the transformation matrix from B1 or X1, Y1, Z1 to X0, Y0, Z0. And we said X0, Y0, Z0, or the fixed is our fixed frame, basically, is or representing a fixed frame. And remember the whole procedure. So whenever you want to find the transformation matrix from one frame to another, right, you always start with the, wherever the second one is. It doesn't matter. Well, it matters. Just keep that in mind. But bring it all the way back to where the first one is and make the axes align with the first coordinate system's axes. And then start playing around with rotation. Fix the rotations first, right? Once you're comfortable with rotations and the rotation is basically taking care of where the axis or those axes should be at the end, do the translation and move it where it is. Right? So that's pretty much how you can take care of that.
Dr. Masumi?
Go ahead, Lisa.
Yeah, I just have a quick question. Can you go over again why we, remember when you said when you go to the second joint, you have to take into account the rotation of the joint?
So are we talking about part A or part B? Just to be more specific, I guess.
I think part A.
All right. Yeah, I guess both of them has it, but let's just stick to part A. Right. So I said, well, the thing is, you have a revolute joint that can rotate, right, itself, like V0. I started teaching dynamics. I'm still in V as velocity. V1 as rotation, right? Now I said, well, if we start from, you have these, so let me just clean things up. If we start from, I think you have time to be actually patient with these. If we start from where we want to go from, that's where x1, y1, and z1 is, and it says go from v1 to transformation matrix. So this is where we start. And start from where the first frame is. Right? You put the second frame on where the first frame is. Right? And I said, well, this is going to be y1, this is going to be x1, and this is going to be z1. Now, if I can get this to work. Now I said, well, you have to do one rotation to typically 90-degree rotation. But since now the previous example we had here, it's just a point and it's a fixed axis, right? We're not talking about any robotic arm. So it's kind of straightforward. You relatively at this, I would say, compared to the next one, is straightforward. You make rotations, make sure that the orientations of your coordinate system are correct, and then do the translation. Now, what happens when you're dealing with the robotic arm is that you have to make the rotations, those 90-degree angle rotations. Sometimes you might have to do 180 instead of just flip the whole thing 180 degrees. You might end up doing it in some cases. But you do these 90 degrees, or I would say multiplications of 90-degree rotation, like 90 degrees, another 90 degrees around different axes. And remember, these rotations happen around the your first frame axis. But then when you're dealing with a robotic arm, you also have to take into account the rotation for rotation or translation for the type of joint that you're dealing with. So if you're going from this fixed, let's say this one that is fixed, this x naught, y naught, z naught, this one, right? If it's your fixed frame, you can think about it as G. If you're taking this to where it should be, right, the green one, aside from doing those 90 degrees rotation, you also have to take into account the rotation in your joint. So in this case, where the x1, y1, z1 ends up being is not only you have to make the orientation right, you should also remember that this v1 can rotate, right? This one here. I didn't put it there, and that's why I put these two figures together. This one rotates v1 amount, right, in positive direction. If your thumb shows the axis of that joint, positive direction, it rotates v1 amount. So you have to take that v1 also into account. And that's why it gets a little more tricky when you're dealing with robotic arms instead of just a coordinate system. But that's what we did here. We said, well, let's rotate about x naught for 90 degrees, right? This is x naught. We did a rotation for this about 90 degrees, and it turned out to be this is going to stay x1, this one is going to be y1, and this one is going to be z1, right? Green becomes red after 90 degrees about x naught. Now, this gives you the correct orientation, except that since you have v1 rotating, so that v1 is going to also, it has to be taken into account because you have a revolute joint. And the same story was for part B, that pretty much we did the same thing. We said, well, if we start from where we are, right, in that case, x1, y1, z1 would be where you start. So you put your x2, y2, z2 exactly aligned with that, x2, y2, z2. You have to make the orientations right first. Maybe the third example I give is less confusing. So the problem with this one is that it is showing the axes after the rotation of those joints. Right? Sometimes you get it in the next example I'll go over after we're done with this, the third part of this. You'll see that actually it doesn't show where the axis is after the rotation of that specific joint. It just tells you where it is, and you have to take into account the rotation of that joint. Now, so this is the procedure. You go through those 90 degrees rotation, or multiplication of 90 degrees rotation, could be 180 degrees, positive or negative, whatever you end up thinking that you can make this correct. Then you take into account the motion of the joint that your axis is attached to. Right? So in this case, you want to get into x2, y2, z2. Well, you have to do, I think, two. That's what we did, right? 290 degrees. I should have it here. It's probably nicer. I had to do 290 degrees and then take into account the rotation for my joint. And remember, the order is always the same. Do those 90 degrees rotations, right, to make the orientation, the orientations right. And now, in your mind, the way you can think about it is that imagine that joint hasn't moved yet, right? That would be just these two first steps. And then make the rotation, make the whatever motion that you have for the third joint. Right? In these two cases, we have revolute joints, so you have to take into account the rotation for the revolute joint. You'll see for the third part C, we are going to a translation or I just escaped my mind. Translational type of joint. It's embarrassing. I don't remember the name of the joint. That you only take into account the translation, right? For the third point, you'll see that. But the procedure is always the same. Always go over 90-degree rotations to get the general orientation right. And at the end, take the rotation or translation of the joint into account, right? That would be your rotation, and do the translation. So all the rotations, starting with 90 degrees, then the joint, and then the final translation. And that'll give you, I think, a relatively straightforward path to go through. If you start messing with this and you start taking into account the joint first and other rotations later, things get lost there. That's my experience. So I do it this way, and I suggest you do it that way. I don't even know if I answered the question, Lisa.
No, it definitely makes more sense. Yeah, thank you.
I just started somewhere, I end up somewhere that I'm not sure. All right. Let's do, okay, let's do part B in a different approach, right? Let's call this approach 1. Right? Remember, we wanted to go from x1, y1, z1 to x2, y2, z2. Right? So we started, in this case, we did a rotation. Hopefully I can follow what I did here. I did a rotation about z1 for 90 degrees, right? The green, light green that I did there. So what happened? We ended up with the light green, x2 upward, z2 still along, z1 and y2 to the left. And then that one, I made another rotation about y1. Remember, all the rotations, you have to do them about the axis of the original frame, like the first frame. I made another rotation about y1, the orange color there. So the green, bright green, becomes the orange axis. X2, do I do it? Yes. So Z2 comes. Why did I put 2 all the way on this item? This is Z2. So Z2, X2 upward, and Y2. Now, this is the general orientation you get with those two 90 degrees angle. Now, the last step would be you have to take into account you're going from X to Y2, Z2, right, in orange, to now X2, Y2, Z2 in magenta, I guess, color here. So for that one, you need to have another rotation V2 amount about Z1 axis again. So if you do another V1 here, you will get your axis. See if I can draw it here. Then your axis become like this, right? And that's where your look at that. What do you do? 10 colors ontology. This one, and this one. So this becomes your eventually Z2, X2, Y2. All right. So the final, I would say, nudge that to take into account the rotation of your joint. Now, why do we do this? Because remember, at the end, what happens that those 90 degrees are fixed. But when this arm is moving, right, what is changing? You don't want to rewrite your transformation matrix like every time for every given angle. You want to get the general equation for this. Now, once you do this one, you get a general equation that for any V1 during the V2, I should have said, I don't know whether to say V1 there, the rotation there is V2. Sorry about that. So when this arm moves, right, at any given moment, you want to know your transformation matrix for any angle that that arm is, or that a specific revolute joint is rotating. Now let's do a different approach. Let's call this approach 2. Right? Now I'll bring the same, if I can find it on my computer. I think it was this one. I don't know why it came so small. It's a little bigger. So let's do this again. I gotta remember, we are going from part B. We are going from B2 to B1. Right? These two here, right there. I'm not gonna make it messy. I'll just try not to. Let me see if I can make it even bigger. I'll write in the next page, the procedure. So I want to go from X2, Y2, Z2, X1, Y1, Z1 to X2, Y2, Z2. Right? The first approach, we did that. We made a couple of rotations. I don't know if you went home and thought about this, but there is a second way of doing this. Right? The first one, I started from a rotation about Z1, rotation around Y1, and then taking into account the rotation of the revolute joint. Now, there is a second way of doing this. Let's see if you can follow. So here is, I'm going to make things a little bold. So let's take this as X1, Z1, Y1. So it's as big as it can be. And we are going to start with, and remember, we want to get into X2, Y2, Z2. I'm not going to draw on that. I just want to bold X1, Y1, Z1. Right? Now, I'll start with, well, that's where we start, right? That's start with assuming that we have it exactly aligned with X1, Y1, Z1. So this is X2, Y2, Z2. Now, I'm going to do a rotation about...
Sorry to interrupt, but I see in the picture that where Z1, you have Y2 as well. And then Z2 is next to X1.
Yes. So that's okay. So did I make?
So that's confusing me. Like I don't know what's going on because like this is a little bit confusing.
All right, I can get rid of that. There you go. If I can, there you go.
Oh, okay.
Or maybe I want to keep it there though. Okay, so let's just get rid of that and stick to what we have. There you go. If I can find this one problem, this. Bear with me, folks. I'm gonna get a hang of this. There you go. Found that. Good. All right. So hopefully it's better now. So we have x1, y1, z1, and we start x2, y2, x2, y2, z2. You know where it is. I'm not going to put it there to make it confusing. We start with x2, y2, z2 aligned with x1, y1, z1, right? And we want to get into, these axes, right? This one, not with this one, this one, and this one. I'll remove it. Just want to mention that what direction is already z2. You want to get into these axes. I'm not going to mess with them. Let's follow these steps now. As I said, I want to just go over the second approach to get into those axes. Now I'm going to make a rotation about y1 for 90 degrees. All right. So this is my first rotation. I'm going to do it green and hopefully right. I'm going to make a rotation about y1 for 90 degrees. So if I do that, this gets here. This becomes z2, this becomes x2, and this is still y2. Right? So this is z2, this is x2, this is still y2. So this is 90 degrees about y1. And then I'll do a 90 degrees about x1. Right? Here. I'll do a 90 degrees about this one then. So that'll take my axes. I'll take y2 here, take x2 there, and z2 stays here. So there you go. This is where your z2 was, so it stays here. 90 degrees, so this becomes your x2, this becomes your y2. There's no way of me making it less, I guess, crowded. That's just how it is. So 90 degrees about x1. Right? Now I have my axis. Right? Just to remind you where everything was and where I want it to be. I'll bring it here again. Compare where, let me make it bigger. Almost there. There we go. So compare where x2, y2, z2 are, like in the final position, and where we are, right? In orange. x2, y2, z2, and you have x2, y2, z2. Right? We got it almost there. Now the only final nudge or rotation we have to do is the rotation about, again, z1, right? This one. I have to make another rotation as the final rotation around this, which is basically the rotation of this joint, V2, to get my axis right. If you do that, you're going to end up getting into, it's already crowded there. So you just need to rotate the orange. I started from gray. I did a rotation. I'll write it here. Rotation about y1 90 degrees. I went from gray to green, orange, bright green. And then I made a rotation about x1 or 90 degrees. So the orange was the final position after 290 degrees rotation. And then I nudged it a little bit to get into where the axis is, because I have a revolute joint. I have to take into account the rotation of that revolute joint. I'm going to give you a few seconds or more maybe to just think about this.
So let me get this straight. You rotate it 90 degrees about X, 90 degrees about Y, 90 degrees about Z in order to align X1 with Y2. Y1 with,
No. So
was it Z2?
so I started from the black one is the first axis, first coordinate. I keep it fixed. No, now I want to get, and the black one is x1, y1, z1. I want to get into x2, y2, z2. Right, these axes here. I didn't put it there because it was already crowded. So x2, y2, z2. I want to get into these. Now, in order to get into these, I have to start to find my transformation matrix. The process is I have to put the second frame exactly where the first frame is at the beginning. And that's the gray color, frame in the gray. x2, y2, z2, which is aligned with x1, y1, z1, right? Nothing has happened. Nothing has happened yet. Now, I made a rotation about y1 for 90 degrees, positive. My thumb shows the axis y1. So I'm making a positive 90 degrees about y1. So the bright green becomes where the axes are after that 90 degrees rotation about y1. You go from gray to bright green. Then I'll do another rotation about x1 now. I remember rotations are happening always about the first frame. So about x1 for 90 degrees. So the bright green rotates 90 degrees about x1 now. It becomes the orange axis. Because x2 comes up, y2 comes down, and z2 just stays where it is because rotation is happening around that. Now, after 290 degrees rotation, I get the orange axis. Now, the orange axis is pretty much, I went through all rotations needed. I have to make that revolute joint into account at the end. Right? So I'm nudging it up a little bit around Z1 because that's where the axis of this is. And this axis is Z1 pretty much. Right? If you look at this one, this is just Z1, the first frame. Right? It's fixed. This one. If I rotate V2 amount about that, now I'm taking into account the revolute joint. So all the rotations I needed are done. And since two axes have the origins on top of each other, if you look at x2, y2, z2, and x1, y1, z1, there is no translation there. So I don't need to be worried about the translation. If there was a translation, I had to take that into account. So I'll give you again another minute to just think about this. How did these rotations happen?
So am I right in assuming what I assumed, or am I wrong?
I was actually lost with over there because you told me 3 rotations, 90 degrees rotation, but there were not three. That's what you were saying?
Well, in order to get to the point where, can you go back a slide?
You're talking about this one, right? Or so
yeah, let's just assume that we're starting at x1, y1, z1, right? And we want to get to x2, y2, z2, right? So in order to get them aligned with each other, let's say, I know that with the part that's highlighted in orange, it's offset a little bit, right? But in order to get them aligned with each other, you would have to rotate 90 degrees about x, 90 degrees about y, and then 90 degrees about z, right? And then you'd have y1 aligned with x2, x1 aligned with z2, okay, so, and z1 aligned with y2, right?
Let's do the rotation that you were saying. I want to know where does it go. So we are here, right? Originally, let me draw it separately. We are not in a rush. So this is x1, z1, y1, right? This is x1, y1, and 0. I'm going to start with x2, y2, z2 being aligned with this. I just want to follow your steps. See where we end up. X2, y2, z2. So now you're saying make your rotation. Can you go over the steps again? So we'll do it here one by one.
Rotate 90 degrees about y-axis.
Well, which y? Y1, right? So 90 degrees about y1, right? That's pretty much what we did. This becomes, oops, this becomes z2, this becomes x2, and this becomes y2. So this becomes z2, this becomes x2, this is still y2. And then what's the next step you mentioned?
Rotate 90 degrees about x.
Now rotate 90 degrees about x, right? Just pretty much.
Wait, is this in terms of when I say rotate 90 degrees about x, is it always going to be x1, right?
Yes, it's always, rotation is always have to be mentioned in terms of the first frame, the original frame.
In terms of first frame. Okay, yeah, so 90 degrees about x1.
So that one becomes, it gives you this one. Let me just write longer. This one and this one, right? It makes it Z2 stays there, X2 goes there, and Y2 comes here. All right. So what is
you know what? Now I see where I went wrong because I added too many rotations.
Yeah, that's what I was saying. I feel like the third one is extra.
Yeah, I added too many rotations. Two is enough, and we're almost where we need to be, right?
Yeah. So now you're good, right? After this, we just take into account the joint. We just do.
Okay, now I see. Okay, thanks for drawing it out for me.
This only gets resolved by just actually doing it and see where the axes go. Can be a little frustrating, but I suggest you try to draw it mentally. When you have more than one rotation, it's hard to imagine, at least for me.
It's like guessing where the colors go on a Rubik's Cube.
It's actually a good example. Yeah, I agree with that. It's a little, I'm not a very smart person, so I have to draw it and figure it out. You guys usually have better brains and smarter, so.
So this was very helpful going through it. But then the one step we have left is to move around the Z1 just enough to match the angles that we have in the original.
Exactly. So
all right,
like this, right? And that becomes the final one.
Perfect. Thank you.
This becomes still Z2. Then this is your X2, and this is sorry, your Y2. This is Z2, and this is X2. I messed it up there. That becomes your, you kind of know it at this point. This is your Y2. Orange gets into the purple. Right. Yeah, so as I said, I'm not a pretty smart person. I prefer to draw it and figure it out. And it only comes to you. Remember, these steps you have to figure it out. I'm giving you the steps right now, but at the end, you are just given the first frame and the final frame. So you have to start thinking that you have to be able to see what happens if you rotate in that direction, and relatively have a plan and do a couple of rotations here and there, see which two rotations, typically two, takes you where you want to be, right? And again, drawing, I strongly suggest drawing. It's much easier. But maybe if you practice enough and like me, you're not jumping from one course to another, I think you do actually yourself multiple courses, but what comes to you easier. So let me just write down the steps 1, 2, 3. That's the color code I was using. So basically, step 1, I did a rotation about 90-degree rotation, 90 degrees rotation about y1, right? Which basically is r y1 90 degrees. 2, another is the orange one, so it's 90 degrees rotation about x1. Everything is about the original frame, 90 degrees. And the third one would be just the rotation to take into account for the joint. So V1 rotation about Z1, right? We did about Z1, so that becomes R Z1 90 degrees. No, what did I do? R Z1, and that's not V1. I don't know why they keep referring to it as V1. That rotation is V2, right? This rotation. Hopefully you caught me there and you realize that. V2. And you can just write this now. Once you have all the rotations, there is no translation. You know, the purple, the magenta color is basically the original position, final position of your final frame. So you do the procedure. Remember, you start from the last one. So your rotation from 2 to 1, or the rotation that can give you the coordinates of frame 2 and frame 1 is, right, start from the last one. So R Z1 V2 multiplied by R X1 90 degrees multiplied by R Y1 90 degrees. Do it 2 by 2. All of them are 3 by 3 matrices. So you do X1 90, Y1 90 degrees, and then do V1 Z1 90 degrees. I don't know if you have time. I can try to write the matrices here just to remind you. R Y1 90 degrees. Actually, it's easy to write because it's cosine 90 degrees. So it comes 0, 0, 1, 0, 1, 0, and then minus 1, 0, 0. And that R X1 90 degrees is so X1 is cosine. So this becomes 1, 0, 0, then 0, 0, minus 1, and then 0, 1, 0. Hopefully I got the right cosine sign minus. And Z1 V2, I can just write it here. R Z1 V2 would be rotation around Z. So you start from cosine V2 minus sine V2 0, sine V2 cosine V2 0, then 0, 0, 1. You do the matrix multiplication, you can get R to 1. I should have that answer, so I can just give it to you later on. You can double check. So R2 1 eventually becomes, if you do that matrix multiplication, you should get minus sine V2 0 cosine V2, and then cosine V2 0 sine V2, and then you get 0, 1, 0 there. Which is pretty straightforward. And then
Professor,
since you,
can you go back to the previous slide real quick, please?
Sure.
Thank
and
you.
Then, and since you don't have any translation, your D vector basically is going to be 0, 0, 0, right? The origin of the second frame, position of the origin of the second frame, magenta color in the the position of that, the coordinates for
That's
the
good,
position
thank you.
of that in original frame, which is 0, 0, 0. Right? So your D in frame 2, you can call it D1, 0, 0, 0 transpose. Put everything together. This gives you the transformation matrix. Right? It's pretty much your rotation, translation, bunch of zeros. You don't really care about those parts, and just 1. And just minus sign V2, 0, cosine V2. This is 0, cosine V2, 0, sine V2, 0, 0, 1, 0, 0, and then 0, 0, 0, 1. That should basically be your matrix. All right. All right. Now let's just add the last one. You would probably imagine where am I going with this. I want to go from the frame before last one to the last frame, right? So part C, you can write it as if I can get this to work. Part C, write it this way. Just say a transformation matrix from, how did we phrase those? Transformation matrix from B3 to B2. The transformation matrix from B3, which is basically X3, Y3, Z3 to B2, X2, Y2, Z2. All right. Just want to wait a few seconds if someone is taking notes on this slide. So that, again, I'm going to bring the figure here. Just move this and bring the same figure here. You're sick of it by now. So in this case, you are here, right? It's X2, Y2, Z2. This is X2. This is Z2. This is Y2. And forget about the rest of the story there. You don't really care about those. See if I can actually erase them from there so I can get distracted with those. There you go. And you want to go to X3, Y3, Z2, right? At the tip. Now, this case, I think it's pretty much the easiest case. There is really no rotation. If you look at that frame in and you bring it align and put it aligned with your frame right now, and this is, let's say, the original position, Z2, Z3, X3, Y3, you'll see that there is no rotation. We basically slide it over to where it is. So there is only translation, and that translation would be just taking into account this joint, right? So if I want to write this, I will say no rotation is needed. So let's just write it this way. T3 to 2 would be R3 to 2, D in 2, 0 and 1. Right? That translation, that D would be basically the translation you're taking into account for that joint. So once you get to this point, right there, you're basically just doing a translation. The way you can do this, you can think about the rotation about any axis, Z, 0 amount. So you can think about this R this one right there as, let's say, R rotation about Z to 0 amount. Once you have 0 rotation, doesn't matter which axis you take into account. It always gives you the same matrix. Right? You plug in 0 for any rotation matrix, you should get the same matrix. So that becomes, if you do Z, or it's a pure translation. So 1 0 0 0 1 0 0 0 1. There's no rotation there. And the translation is basically just D3. So you can write D also as D2 would be, remember, it's along Z2 D3 amount. So it's going to be 0 0 D3 transpose. So I'll get T32, relatively easy matrix. Just basically, I put all those 1 0 0, and the next one is also 0 0 1 0 0 0 0 1 D3 0 0 0 1.
Question?
Go ahead.
So we need that identity matrix, or
Oh yeah, we need that.
we need that.
Because we need to have a 4x4 matrix that is invertible, I would say, if you want to.
If it were all zeros, then the whole thing would be, whatever you multiply by it would be 0. It would just cancel out any rotations in the adjacent matrix.
I didn't get the question, Lucas. Can you say again what?
The whole thing where she was like,
No, I was just saying that if there were no identity matrix, if it were just all zeros,
Yeah,
if you multiplied this T by another matrix, it would like
it makes
it would
everything
make
zero.
any terms, it makes everything zero.
like she didn't really want to.
It makes every translation or any position that you want to go from one frame to another makes it 0. So you need that identity matrix. Identity matrix basically is just, you can just memorize it that way. If there is no rotations, identity matrix. You don't want to memorize it in any rotation matrix equation, XYZ around XYZ, any of those, put theta equals to 0, gives you identity matrix. All right. Now, so we did this in ABC procedure, but imagine if now they tell you find the transformation matrix from B3, right, from B3 to B0, if that's the question. All you got to do is just multiply these transformation matrices. Right? Almost there. If want to find transformation from 3 to 0, right? You have a coordinate of you know the coordinate of a point in the final frame. You want to find it in the fixed frame, base frame. You just do the multiplication of what you got, those matrices, and that gives you that. So you have like 3 4x4 matrices. You already calculate that between each two frames. At the end, you just multiply it together and gives you the transformation matrix from the final frame to the base frame. All right, that's just you know. And it between any two frames, you could just be asked that find the transformation matrix from B2 to B0. So if you want to do that, you have to find transformation matrix from B2 to B1, and from B1 to B0, because you only work between, can work with 2 frames at a time. So find 2 that are next to each other, and then another 2 that are next to each other, and then you just do the multiplication between transformation matrices, right? All right. Wow, way slower than I thought I would. Yeah, I knew I'm not gonna have extra time. Kind of lie. Folks who know me, they know that we never have extra time in classes. Pretty much it never happens. All right, so the last one, I'll go over this quick because I want to actually do this as well. Let me bring it here. That quiz for a different quiz. Figure 2, there you go. So this is the figure right there. X2, Y2, Z. For some reason, the source I took these from the axis of represented by the smallest font possible. The problem statement, you can say it's a robot manipulator. I'm not going to write that part. These coordinate frames that are given. You're asked to find the transformation matrix from B3 to B1. And so find, that's what I was talking about. Find the transformation find the transformation matrix from B3, which by that I mean X3, Y3, Z3 to B1. There is a B not here. We can just refer to it as G if it makes it better. G X1, Y1, Z1. So this is basically 2 steps in one shot. So we have, here we are. We have to go from X1, Y1, Z1 to X2, Y2, Z2, and from X2, Y2, Z2 to X3, Y3, Z3. Right? So we have to do 2 steps. But general procedure, if I want to write transformation matrix from 3 to 1 is equal to transformation matrix from 2 to 1 times transformation matrix from 3 to 2. Right? So all I got to do is to find a transformation matrix for each. Same story. Let's start with 2 to 1. Right? 2 to 1, I'll write it here. T2 to 1 is obviously is equal to R2 to 1, D in 1, 0 and 1. So I have to find the same process. I have to start with where my X1, Y1, Z1 is. Right? I am going to put X2, Y2, Z2 exactly where that is. So this would be X2, Y2. Maybe I should follow the same color code that I was doing. So later on, if you're looking at this, start with gray. Not probably the best choice of color I did, but since I chose that, I'm just going to stick to it. X2, Y2, and Z2. Right? And I have to get to where X, well, I have to make the orientation right. So can you tell me what is the 90-degree rotation that I have to go through? That's a good example.
About the X one.
So I have to go rotation about X, 90 degrees. How much I have to rotate?
Yeah. Is it 90 degrees or negative 90?
Negative 90 degrees. Yeah, that's what I was trying to get. Right. So I have to do negative 90 degrees. Remember, thumb, your thumb shows the axis, 4 fingers shows the positive direction. So if you're going in the opposite direction around that axis, it should be negative. Right? So if I do a rotation in this way about X1, I will get this is still the same, so that is going to stay X2. Don't put the X1 there. So we do the rotation, X2 stays there. If I do the negative, Z2 comes here, and this one goes down here. So this becomes your Z2, this becomes your Y2. Right? So pretty much you got the orientation right. But see, this problem is not representing now, it's representing the axis just in 90 degrees form. But you have to still remember that you have this V1 there. Right? So the second rotation you have to add to your rotation, although it's not clearly represented here, but you do have that degree of freedom and you do have that rotation. So you have to take that into account. Previous example, it was I guess in some sense nice because it was showing you where it goes if we rotate a little bit, but this one doesn't show. Still remember, it's a robotic arm and it's moving. So going from to X to Y to Z2, you have to take into account that V1 rotation. So in this case, you're going to get two steps. Your two steps would be step one, minus 90 degrees rotation about X1. Right? We did the rotation about X1. And then we pretty much orientation is there. We just have to take into account the rotation for our joint. So rotation, let's go to V1, rotation about Z1. Remember, every rotation occurs about the original frame, original position of the frames. And we do have the translation. We have to go from where we are to where we should be, or we can think about this: where is the origin of the final position, this point? What is the coordinate of that in X1, Y1, Z1, the original frame? Right? And that's basically just D2. So the last step would be, I'll just write D1 is equal to D2 going up. So the three steps that you have to go to get into to get your transformation matrix. Right? These I can actually write it here. This one it's an easy one, or X1 minus 90 degrees. So that becomes cosine. It becomes 1, 0, 0, 0, 0, 1, 0, minus 1, 0. Right? That gives you this one. Rotation about Z1. After I should write it. So I have no other choice but going to next slide. So I'll write R. What was that? About Z1, V1 amount. So that will give you, you have Z1, so cosine V1 minus sine V1 0, sine V1, cosine V1 0, 0, 0, 1. And then you got your D1 as, remember, everything is in the original coordinate frame. So your D2, basically, the translation you get is in the Z direction, right? Look at where Z1 is, and you're going up along Z1. Everything in original coordinate frame. So this becomes 0, 0, D1. I can show it better. D3, I guess. That's what it used. No, D2. Even getting notations. So transpose. So you do the multiplication, right? Your final R from 2 to 1 becomes, I don't write it here. So it becomes R Z1. We start from the final rotation, go backward, or X1 minus 90 degrees. You do that, that'll give you R. And then you have D. I'll give you the final transformation matrix. Just basically a 3 by 3 at the top is your rotation. Then you have your translation, a bunch of zeros, basically. So T2 to 1 becomes, let's put it this way. You have your R at the top. Your R becomes cosine V1. You just get a 0 in the middle, pretty much, minus sine V1 0. This becomes sine V1 0, cosine V1 0, 0, minus 1, 0, D2, and then 0, 0, 0, 1. This becomes your D2 to 1 transformation matrix from B2 to G in this case. Now, the second thing you have to find is right here. So we found this one. Obviously, it's not what I meant. We found this one. Now we have to find this one, T3 to 2. Right? If I bring it, I'll just wait a few seconds. That one is, I think it's.
You go back for a second, please.
Yeah. Mm-hmm. Yeah.
From coordinate system 1 to coordinate system 2, why does it get flipped like that?
Oh, you mean why they put the coordinate this way, coordinate this way? Why didn't they just put it upward? That's what you mean?
Yeah.
We don't really discuss that at this point. We'll see later on how to decide about the orientations, right? This is just what we are given. Right? Would it be better if y2 was upward and we didn't have to do this rotation? You will see later on there are some good reasons for playing around with orientation, because when you do these matrix multiplications, you might end up with a matrix that you can make it simple using some trigonometry relationship. That's where the Deneved-Hartenberg method comes into play, and we talk about how can we actually decide about the orientation of axes. For now, just take it as is. There is no really.
Okay. The only reason I was confused was because, there's not much going on between 1 and 2 except translation and rotation about the vertical axis.
Yeah, you could.
So I was wondering where the flip came in, but if that's just given, then okay.
Yeah, that's just given. Again, you'll see later on that there is a little bit of logic there because we are dealing with matrix multiplications. So sometimes a little bit of nudge, moving things around. Because now you see this is flipped, right? Now, because this is flipped, going from 2 to 3 becomes easy. If you had it the other way, going from 1 to 2 would have been easy. But then going from 2 to 3, you still had to make a rotation. So you had a choice there that make it easy to go from 1 to 2 or make it easy to go from, making easy is a very loosely term I'm using probably. Loose term that not technically correct. But it's easier to go from 2 to 3 because now your 2 and your 3 have pretty much the same orientation. All you got to do is the translation. If you chose to do translation from 1 to 2, then you had to still do a rotation from 2 to 3. So that's at some point you have to deal with it, and that's I guess that might be the reason they probably put it that way. I don't know if it makes sense what I'm saying there. Hopefully it does. All right. So let's go for T32. All right, let's bring it here. Again, this one. I can do it again. So if it's bigger, there you go. This is easy. All right, this is you have x2, y2, z2. You start your x3, y3, z3 where your x2, y2, z2 is, or where they are. It's x3, z3, y3. And since you did that rotation already from 1 to 2, now all you got to do is just the translation d3 amount. Right? Going from where you are to where you should be, it's nothing but the translation. Or you can think about it this way: the origin of frame 3 is coordinate in frame 2, which basically is just d3. So d, that's what I'm trying to say here. d3 to 2 is, that's a very ugly shape matrix. This would be R3 to 2, D2, 0, 1. Right? Get that there. Now this one, there is no rotation there. So as I said, you can just choose one and one of the rotation matrices, put 0, or you already know there is no rotation there. You just say, well, since there is no rotation, it's just an identity matrix. Right there. And your D2 becomes, you have translation or have translation about Z2, everything about the original frame. Right? So that would be 0, 0, D3. So your transformation matrix from 3 to 2 Well, again, it's an easy matrix because there's really no rotation there. So it comes start with 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, bunch of zeros here. Then for the last column, 0, 0, D3, 0. I have to remember to put transpose here. Right. There you go. Right. Now that you know T 3 to 2, you know T 2 to 1, all you got to do is to just multiply these two matrices. Right. That's what we wanted. If you remember beginning, here we were. That's what we wanted to find, T3 to 1. Right. Now we know what T 2 to 1 is. We know what T3 to 2 is. We just do a multiplication of two 4x4 matrices and you'll get your T3 to 1. So sometimes you're given information to go from one frame to multiple frames away, but remember, the tool you have only works for 2 frames next to each other, or the way we analyze it. Right? It's always going to be like that. Even later on, when we talk about more classic methods or organized methods that they use in robotics. We always deal with pairs. So you have to deal with first pair, second pair, how many pairs you have to take into account to get into where you want to be, find all the transformation matrices, and then just do multiplication. So in this case, T 3 to 1 becomes T 1 to 2, 2 to 3. If you do that multiplication, I give you the final answer. You want to check. Well, basically, 0 comes here. Cosine of V1, 0, minus sine V1. Sine V1, 0, cosine V1, 0, minus 1, 0, 0, 0, 0. And I think the last column becomes minus D3 sine V1, D3, yeah, cosine V1, D2, and 1. Just do that operation, multiplication, and make sure actually you can do it. This is T32, this is T21. You should get this. Hopefully, if I did not make any mistake, I'm going to double check. I don't think so, but you can never be sure 100%. So life is about probabilities. All right, folks.